Hi there, my name is Brandon Treese. I'm a Solutions Marketing Manager here at NI. In today's video, we're going to be talking about the challenges associated with incorporating digital avionics interfaces into test stations used in manufacturing and depot test applications. And specifically, we're going to be talking about the performance characteristics of using an FPGA-based solution for digital interfaces. So to help me with that today, I'm joined by Nathan Johnson-Williams, a digital design engineer from New Wave Design and Verification. So Nathan, welcome.
Thank you.
So let's just start by framing up the discussion and taking a look at what we're showing here today.
Sure. Today we're using the NI7902 that has a user customizable FPGA to test, verify, and interface with 10 gig Ethernet. 10 gig Ethernet is showing up more and more in modern avionics and has some unique challenges in test and verification due to the high bandwidth. We're going to be using the FPGA to address some of those challenges and improve performance.
Okay, so when we think about all the different protocols that could be used in an aircraft, you know, ARINC 818, S3O, fiber channel, whatever it might be, of all those, Ethernet seems like it's pretty well figured out. I can just go buy a NIC card off the shelf that does 10 gigabit Ethernet. So why is that not an acceptable solution?
So you're right. 10 gig NICs are prevalent. They're available in a bunch of different form factors. The difference comes in at precision and consistency. So a 10 gig NIC is going to be closely coupled with software and designed as an interface. It may not have the consistency and repeatability that you'd expect from a test card. And that becomes important when you start dealing with precise data flows or timing regulation. For that, you might want to use an FPGA because it's going to be able to more accurately reproduce the data patterns and timing characteristics that you need in your test setup.
Okay, so maybe you can show us why that's a challenge here today.
Sure. So we've got a couple examples that we can run. The very first one we're going to do is show a timing-driven one. So in this case, we've got the timing characteristics driven by software. We're going to do a simple test where we're just going to send out a 1 hertz packet, so 1 packet every second. And we're going to see just how consistent it is, repeatable it is. I'm going to run this VI, and we're going to capture some data on our network analyzer here. So if we look at the data, it's not quite 1 hertz. Sometimes it's a little over, sometimes it's a little under, and there's a fair amount of jitter. So we're looking at a couple hundred microseconds of jitter per frame. So it could run a little faster, it could run a little bit slower. In a lot of cases, that doesn't matter. It's a bigger deal in 10 gig Ethernet because of the data rates we're talking about. 100 microseconds corresponds to a couple megabits of data, and that makes a big difference over the course of a test. If we scale this up to do 4 channels, the problem gets even worse because software has to juggle more tasks with everything else that it's already doing. So let's grab a couple scope captures of 4 channel and see how that changes. So we're going to look at port 3. So the accuracy has gotten even worse. Now we're talking not a couple hundred microseconds, but even up to a millisecond. Now we're talking plus minus a couple hundred megabits of data. And in a precision 10 gig test, that matters a lot because it's going to vary from test to test, and it's never going to necessarily behave the same way.
Okay, I definitely see the challenge you're pointing out here with using a software-based solution. The processor definitely is ultimately going to get in your way. If you have 1 channel, it might work, it might not. But as you scale up channels, it's pretty much guaranteed that you're going to have some challenges. So how does an FPGA solve this challenge?
So an FPGA has dedicated hardware resources on the chip, and we can do what's called a hardware offload. So the software will reach out, configure that FPGA, tell it how it wants to behave, and once it says go, it's hands off. That means it has dedicated logic for each channel that has one job and one job only, and that is to be accurate. So let's run this test again using the FPGA to control timing. We'll grab a couple of frames on the logic analyzer and see how it did. So already things look a lot better. Our accuracy is within tens of microseconds, if not microseconds, and our jitter is also drastically reduced as well. If we scale that up to run multiple channels, because each channel has a dedicated bit of logic, we're not going to see any performance degradation. So your scalability is much better. You can do multiple channels, even multiple cards, which would be a nightmare to try to handle in software. In this case, let's look at port 4. You can see we didn't see any drastic performance difference. It behaves largely the same way as we did with one port as we did on 4.
Okay, I definitely can see the difference between the software approach to a hardware-timed approach using the FPGA. Now, I'd be remiss if I didn't also say that, in this demonstration, we're using the 10 gigabit Ethernet IP core from New Wave that's built on top of the NI7902 high-speed serial card. And that's all integrated together, so there's actually no VHDL interfacing that you had to do to build this demo.
No, it's available as a turnkey design on the 7902.
Yeah, that's fantastic. That's going to save teams a lot of time in incorporating 10 gigabit Ethernet into test stations. And so I want to say thank you very much for joining us here today. To learn more about this particular solution using 10 gigabit Ethernet, or even other protocols like Serial Rapid I/O, Fiber Channel, and ARINC 818 and more, please go to ni.com/digital-avionics. Until then, have a great rest of your day.